LLMs don't have a thinking problem, they have a memory problem. This week, I read a paper that made me rethink how we are building AI systems. It's called Lossless Context Management from a team at Voltropy. And the core idea is simple but devastating. We have been solving the wrong problem. Everyone right now is obsessed with making LLMs smarter, bigger models, better prompts, more reasoning tokens. But what this paper shows is that intelligence is not the bottleneck, memory architecture is. Let me explain what I mean. When you build a real AI agent, not a toy demo, a real one that needs to work across multiple sessions, handle large code bases, process data sets, you hit a wall first. That model starts forgetting things. It contradicts itself, it hallucinates constraints you already defined, and your first instinct is, I need a better prompt. But prompt engineering doesn't solve this, it hides it. Here's what actually happening. We are asking the LLM to manage its own memory. Think about what that means. Every time context grows, we do one of the three things. We truncate old messages, we summarize them recursively, and we let the model decide what to keep. All of these are lossy operations. Information gets discarded, and once it's gone, the system doesn't fail immediately. It drifts. This is why you see the agents looping, forgetting task constraints, and producing inconsistent outputs across the turns. The failure are not deterministic. Same input, different output. And that's unacceptable for production level systems. The recursive language model paradigm is different here. There is a prior work on this, a paper called Recursive Language Models from Zhang, Kraska, and Khatab. Their insight was radical. Stop treating context as a fixed input. Treat it as part of the environment. They gave the model a REPL and let it write Python script to manage its own memory, chunking, compressing, recursively processing context however it wanted. This was brilliant though. It opened a new design space, but it also created a new problem. When you let the model write the loops that manage memory, you inherit the stochasticity of the model. A good chunking strategy in one rollout becomes a bad in the another. Error handling, concurrency, state management, all of it now depends on whether the model writes correct code every single time. For research, this is fine. For production, it's a nightmare. So, the architecture centric answer is LCM. The paper LCM takes the opposite approach. Instead of giving the model full control, it depends on operating system for context. Here is the key architectural decision. The LLM should not manage memory. Memory should be managed by a deterministic engine, and the LLM should only be responsible for reasoning. This is same move what happened in programming language design. Early programs used go to everywhere, maximally flexible, but impossible to reason about. Then Disgastra wrote go to statement considered harmful, and we moved to structured control flow. For while, if else, less expressive in theory, far more reliable in practice. LCM does the same thing for AI memory. How it works? LCM introduces two core structures. One on an immutable store and an active context. The immutable store is the source of truth. Every message, user input, assistant response, tool output is persisted verbatim and never modified. The active context is what the LLM actually sees. It's dynamically assembled from recent raw messages and pre-computed summaries of older ones. Here's the critical part. Summaries are materialized views, not replacements. The original data always exists. If the model needs something from the earlier conversation, it can retrieve it losslessly via tools like LCM grep or LCM expand. This is fundamentally different from RAG. RAG retrieves decontextualized fragments. LCM preserves the full conversational structure. Who said what in response to what decisions were made afterward. The memory is managed as a directed acyclic graph. Older messages get compacted into summary notes, but those summaries retain pointers to the originals. You can drill down at any resolution. One thing I really like about this paper is that how it handles compaction failure. You have probably seen this. You ask a model to summarize something and it produces output longer than the input. LCM solves this with three-level escalation protocol. Normal summarization, which preserves the details. Aggressive summarization, the bullet points half the tokens. And then deterministic truncating. No LLM involved, just cut to 512 tokens. Each level is tried in order. If one fails to reduce token count, the system escalates automatically. Level 3 guarantees convergence because it doesn't call the LLM at all. This is what deterministic infrastructure looks like. The model can't break it because the model doesn't control it. Large file handling. Another detail worth calling out is how LCM handles files that individually exceed the context limit. This happens all the time in real systems. Log files, datasets, large code bases, a single file can blow your entire context window. LCM doesn't try to stuff these into context. Instead, it stores files externally and inserts a compact reference, an opaque ID, the file path, and an exploration summary. The exploration summary is type aware. Structured formats like JSON or CSV get schema extraction. Code files get function signatures and class hierarchies. Unstructured text gets an LLM generated summary. The model now has enough information to reason about the file without loading it. If it needs the actual content, it can grab it or read specific sections via normal file tools. So file references propagate through the summary DAG. Even after multiple rounds of compaction, the model retains awareness of every file it encountered earlier. The next thing, operator level recursion. So this is where LCM diverges most sharply from RLM. The RLM gives the model symbolic recursion, the ability to write for chunk in context and manage loops itself. LCM replaces that with operator level recursion. Two tools called LLM map and agentic map. Both apply a prompt to every item in a list in parallel. The model makes a single tool call. The engine handles iteration, concurrency, retries, schema validation all deterministically. LLM map is for the stateless tasks, classification, extraction, scoring. Each item is processed as a single LLM call. Agentic map spawns a full subagent session for each item. Each subagent has access to tools like file or IO, code execution, and can perform multi-step reasoning. The key property here is the input and output are files on disk external to the active context. The model can process datasets of arbitrary size without polluting its context window. This is MapReduce, but with LLMs as the map function and deterministic code as the reduce. Now, the next point is preventing infinite recursion. When you give agents the ability to spawn sub-agents, you create a recursion hazard. An agent delegates its task to a sub-agent with an identical prompt, which delegates again infinitely. LCM solves this with a scope reduction invariant. When a subagent spawns another subagent, it must declare two things: delegated scope, the specific work being handed off, then retained work, what the caller will still do itself. If the agent can't articulate what it's keeping, if it's delegating everything, the call is rejected and the agent is told to do the work directly. This forces each level of delegation to represent a strict reduction in responsibility. The recursion must bottom out. Unlike RLM, which imposes an arbitrary recursion depth limit, LCM doesn't need one. The scope reduction invariant is a structural guarantee of termination. Next point, benchmark results. That's the most important. They evaluated LCM on the OOLONG benchmark, which tests long context reasoning and aggregation. The baseline was Claude code, not a raw model. but a production coding agent with file system access and tool use. Both systems use Opus 4.6 as the reasoning model. At context lengths below 32,000 tokens, performance was comparable. The full input fits in the model's native window as neither architecture provides an advantage. Above 32,000 tokens, LCM wins at every context length. At 256,000 tokens, LCM outperformed Claude Code by 10 points. At 512,000 tokens by 12.6 points, and at 1 trillion tokens by 4.3 points. Here is why. Claude Code relies on the model to devise its own chunking strategy, typically reading files linearly or writing bash scripts to split them. This is flexible but error prone. The model has to correctly implement the logic on each rollout and maintain coherent state access across chunks. LCM delegates iteration to LLM map, which processes items in parallel outside the model's context entirely. The model never sees the raw dataset. It specifies a per item prompt and the engine returns aggregated results. This eliminates context saturation as a failure mode. Next point is zero cost continuity. One more architectural detail that matters for production deployment is zero cost. RLM style recursive approaches have an always on overhead. Initializing the REPL, loading the prompt as a variable, interpreting code, and all of this adds latency even for short interactions. LCM avoids this completely. Below the soft compaction threshold, no summarization happens. The store acts as a passive logger and you get the raw latency of the base model. When the soft threshold is exceeded, compaction runs asynchronously and the summary is swapped into context between LLM turns. The user experiences no additional latency unless context goes so fast that it hits the hard threshold during the compaction window. In practice, this means zero user facing overhead for the majority of the workflows. What this means for AI systems engineering. The LCM paper is not just about memory, it's about a deeper architectural principle. Should we maximize the model's autonomy or should we constrain it with structural primitives? RLM takes the model centric view, give the model few autonomy to act as a general purpose computer. LCM takes the architectural centric view, provides structured primitives that reduce the decisions the model has to make. Both are valid. They represent ends of design spectrum. But here is what the benchmark results suggest. The architecture centric approach is more reliable for production aggregation workloads. And even if models get better at writing their own memory management code, certain advantages of LCM persist. Zero cost continuity is a structural property, not a bet on model limitations. More importantly, deterministic primitives will let you ship reliable context management today without waiting for models to master the meta skill of managing their own memory. If you are building AI systems, here is the takeaway. Stop thinking only in prompts, start thinking in architecture. The future of AI engineering is not just bigger models, it's better systems. Memory, security, control flow, deterministic guarantees. These will define the next generation of production AI. Most people are not thinking about this yet, but they will be thinking soon. Thanks. See you in the next video.